Hi, this is Matt 2021. All of the questions. Let's jump straight in with Matt 2021 question 1a. A regular dodecagon is a 12-sided polygon, we're told. All the sides are the same length and all the internal angles are equal. Now we're asked to think about a regular dodecagon that's been constructed by putting 12 equally spaced points on a circle of radius 1. I've seen one of these before. That's what clocks look like, so I'm going to try and draw a clock, 3 o'clock. Over there, 1, 2, 3, 4, 5, 6, 7, 8 extra points in there. So a dodecagon, 12-sided shape, has got 12 sides like that, I suppose. And we're asked to find out the area of this one. The circle has radius 1, I should mark that in. I'm going to take one of the points I've already got, join it to the centre, and say that's 1. I suppose I could join all 12 to the centre. I think I'll just join the first 2 to the centre, like that. So it strikes me that if I want to find this area, I don't know the formula for the area of a dodecagon. I only met them at the start of this question, I suppose. But I do know the area of a triangle, and I can see a triangle here. I can see a triangle in between those two radii that I just drew and the outside edge of the dodecagon. So the area of that triangle is 1/2 times side times the other side times sine of the angle in between. The angle in between, I suppose that's a 1/12 slice of the pi, so that'd be 360 degrees divided by 12 is 30 degrees. So I need to put sine 30 in there. That's the area of just that triangle there. Okay, that's 1/2 times 1 times 1 times sine of 30 is also 1/2, so that's 1/4, and there are 12 of these that make up the dodecagon. 12 times 1/4 equals 3, so the answer is E. The area of this shape is 3, which is roughly equal to pi. The area of the dodecagon is roughly equal to the area of the circle overall. This is in fact a proof that 3 is less than pi, and it's pretty close to pi as well. Question 1b. We're told that the positive number a satisfies this integral. A appears here at the top of the integral, the upper limit. We're asked to integrate square root of x, remembering that square root of x is the same thing as x to the power of 1/2 plus x squared with respect to x, and we want to get the number 5 out of that. So I can do this integral, so I should go and do it, I suppose. If I integrate x to 1/2, I get x to the 3/2, don't forget to multiply by 2/3, and if I integrate x squared, I get x cubed. I need to plug in the limits, but they're not so bad. They are a and 0, and this is supposed to be equal to 5. I've just done the integral on the left hand side. If I plug in the a, then I get 2a to the 3 over 2 over 3 plus a cubed over 3. 0 doesn't do anything to these terms. Let's move the 5 onto the left hand side. And in fact, I think I feel like multiplying through by 3 as well and writing it highest power first. A cubed plus 2a to the 3 over 2 minus 15 equals 0. Now that looks quite nasty because of the cubed and the power of 3 over 2, but in fact the first term here, this a cubed is just the square of a to the 3 over 2. So in fact, if I write u as a to the 3 over 2, then we have u squared plus 2u take 15 equals 0, which I can factorise. In theory, u plus 5, u minus 3 is equal to 0. So then I want u is either 3 or minus 5, but I think a is positive, so u is positive, so I want u to be 3, because u is positive. So then a is equal to 3 to the, undoing this power up here, a to the 2 over 3. Okay, which is option number C. Right, question C. We're asked about tangents to the curve y equals e to the x. Let's do a little sketch of y equals e to the x first. E to the x goes up through 1, and then it gets larger and larger. It gets steeper and steeper as it goes. That's y equals e to the x. And we draw two tangents. One's at p comma e to the p, and the other one's at q e to the q. I'd like to think about the first one first. So if I mark on a point p e to the p, that's got x coordinate p, and maybe the tangent looked something like Well, that's not a very good picture of the tangent, but hey, we can work out the tangent, right? We know how to differentiate y equals e to the x. That has y to the x is equal to e to the x as well. So at x equals p, the gradient is equal to e to the p. So this tangent line has gradient e to the p, and it goes through the point p e to the p. Okay, so that's y equals mx minus x1 plus y1. So writing this down so that when x is equal to p, y is equal to this other term, and this coefficient of x at the front is the gradient. That's how I like to write down my tangents. We're asked about the point where this tangent crosses the x-axis. So I suppose that happens when y is equal to 0. So that would be when 0 is e to the p, x minus p. I'm going to bring this term inside here as well, this e to the p term on the end. E to the p is not 0, so I can divide by e to the p, and I'll get x is equal to p minus 1. So this is a fact, I suppose, that the tangent to the exponential graph crosses the x-axis 1 to the left of the point of tangency. A is 1 less than p, wherever your point is. Maybe that's something we knew, maybe that's something we didn't know, but hey, we've now worked out that a is p minus 1. That's true for any value of p. We didn't use any property about p, so it's also, I suppose, sort of true for q, that if you look at the point where the tangent is tangent to the curve when x is q, that will cross the x-axis 1 to the left. That's a long way of saying that b is equal to q minus 1. If you don't believe me, redo this algebra on the screen, but with b's instead of a's and q's instead of p's. Anyway, long story short, p minus a is in fact equal to q minus b, because they're both equal to 1. Yes. C. Question D, there's another couple of exponential curves in this one, so we're going to need to draw more exponentials. Let's do a sketch on the left. I need the curve y equals e to the x, that goes through 1, and I need the curve 1 minus e to the x. So minus e to the x flips it, and then adding 1 to that translates it upwards. So it's a curve that comes down, and I think it goes through the origin. I had to think there. When x is 0, this bit's 1, so 1 take away 1, 0. So this one's going to come down. I guess when x is very negative, e to the x is about 0, so this is about 1. So it's going to come down like this, cross over there. We're asked about the area that's bounded by that first curve, the second curve, and the y-axis, which is, I think, this region here, which looks like a triangle on my picture, but is not quite a triangle because two of the sides are curved, not straight. We would like to find that area because we would like to find the area of that region. I need to find this point, A, I suppose, where these two curves cross, so I know where my region is. Okay, let's try setting them equally to each other. We have, I suppose, e to the x equals 1 minus e to the x, if, and then let's rearrange this, bring this one onto the left, divide by 2, and we get 1/2, x is equal to natural log of 1/2. I'm going to leave it like that, even though rearranging it might simplify it a little bit, minus log 2, anyway. Okay, so A on my picture over here is natural log of 1/2. That's a negative number, so my picture's going well so far. That's minus 0.7 roughly. Okay, over there. I suppose I don't need to know that it's roughly 0.7 because I'm about to do some integrals with it anyway. There's some symmetry going on here. That reflection that I mentioned, this region's got reflectional symmetry, I suppose. I guess what I'm saying is I just need to find the area of this top bit. Where to find the area of this top bit, I can think about the top bit as being the area under the e to the x curve minus this rectangle. It's quite a messy picture now, sorry. But I suppose what I'm trying to justify is integrating from a up to 0 to get from a on the left all the way up to the y-axis. I want to integrate e to the x minus 1/2. And you could think about this as the difference between two curves, or as the area under the e to the x curve minus the area of that rectangle. Both are equivalent and turn out to give the same answer, of course. Okay, we can do this integral because we can integrate e to the x. I suppose we can differentiate e to the x. We know that we get e to the x. When we integrate e to the x, we get e to the x, and we can integrate constants. If we do that, then we get this. Now I need to be really careful plugging in 0 at the top. I get 1 because e to the 0 is not 0. And then I need to subtract what I get when I plug in a into the bottom limit, which is this. Okay, and we know the value of a. So it's time to plug that in, and we'll get e to the a is, well, that's perfect, it's 1/2. And then this a over here is going to be natural log of 1/2 divided by 2. Putting that all together, I get 1/2 plus 1/2 of natural log of 1/2, lots of 1/2s. What do I actually want? Well, that was just the area of the top bit. I want the area of the whole region, so I need to remember to double. So double that. If I double that, I get 1 plus natural log of 1/2, which, comparing to the options I've been given, it's pretty close to this one, but it's not this one. It's 1. That's the same thing as 1 minus natural log of 2, which is option B. Okay, 1e. We've got 6 vectors, and each of them is either 1, 1 or 3, 2. Equal probability. I suppose that means probability 1/2 of each thing happening, like a coin toss. Each choice is made independently. Okay, so I suppose there are 64 different things that can happen. 2 possibilities for the first one, 2 for the second, 2, 4, 8, 16, 32, 64 possibilities. Something on the spectrum between all of them being 1, 1, or all of them being 3, 2, or some combination in between. The probability that the sum is equal to 10, 8 is which of these options? So it's not obvious that the sum could be 10, 8. We should try and work out if that can happen, I suppose. If I've got all of them equal to 1, 1, there are 6 of them, so I'll get back 6, 6. That's not 10, 8. If all of them are equal to 3, 2, then I'll get 18, 12, which is also not the vector 10, 8. 10, 8 is sort of in between, so maybe it feels like I could maybe achieve this. Let's find out. Let's say we get m of them to be 1, 1 and n of them to be 3, 2. Maybe that can happen. For some values of m and n, I mean, it's clearly impossible if m is 10 or 17 or something, and it's impossible if m plus n is too big, but let's not worry about that now. Let's say that m of them are 1, 1 and n of them are 3, 2. Then the sum will be the way you add vectors together. Doesn't matter what order they're in, we can add them up to get m plus 3n on the top and m plus 2n on the bottom. I think about taking this vector, 3, 2, there are n copies of it, add those together to get 3n, 2n. Over here, do the same thing to get an mm vector, and then finally add those together to get m plus 3n, m plus 2n. And we want that to be 10, 8. So this now looks like simultaneous equations. I want the top bits to match, m plus 3n to be 10, and I want m plus 2n on the bottom to be 8. I can solve those by doing the difference between those equations. The difference between those equations would give me n equals 2, and then thinking about the top component there, I've got 6 from that 3n, so I want m to be 4. Oh, and good news, those things do add up to 6, so this is possible. It is possible that we could have 4 of them be one thing and 2 of them be the other thing. And I suppose that's what we want. We want 4 of the 6 vectors to be 3, 2, that way around? No, 4 of them to be 1, 1, and 2 to be 3, 2. And if we get that, then the sum will be 10, 8. So how many ways are there to do that? What's the probability that that happens? Well, the probability that any one sequence occurs is 1 in 64, because there are 64 things that can happen and they're all equally likely. How many of those have 4 of them being 1, 1 and 2 of them being the vector 3, 2? Well, that would be the number of ways to choose 2 of them from 6. How many ways are there to do that? There are 15 ways to do that. 6 choose 2, 6 times 5 divided by 2 is 15. 15 ways. Each has probability 1 over 64, So there's kind of 15 different sequences, ways to shuffle those vectors around. 15 different sequences, each has probability 1 over 64, so the total probability is 15 over 64, which is option C. Question F. We're asked about the tangent to the curve y equals x cubed minus 3x at the point a, a cubed minus 3a. And we're going to think about changing a and working out whether that tangent also goes through the point 2, 0. So I've done a sketch of the curve. It goes through the point root 3, 0, which is slightly less than 2 because 3 is slightly less than 4, compare the square roots. So that point 2, 0 is slightly to the right of the point on the curve where it crosses the axis. It might be relevant when we're doing this question. You can do this question algebraically, and I'll give that a go in a minute. But let's start by imagining what happens if we make a very negative and then increase a to see how that changes the tangent. If a is very negative, then the tangent is over here somewhere on the left, and the curve's very steep, so I imagine that the crossing will be somewhere to the left of this root, which is nowhere near 2. And as the curve comes up, I'm imagining that it's still crossing the x-axis somewhere over here on the left. Then we get to this turning point where the tangent doesn't cross the x-axis anywhere when the tangent is just at that turning point. And then on the way down, I suppose it's very shallow, so I'm imagining that the tangent crosses the x-axis miles over there in positive x. And as it comes down, there's a point here, I think, in the middle where I imagine the tangent kind of going through the middle, maybe crossing at 0. So in between somewhere, from this case where it was just coming, the tangent was just coming down, very slightly negative gradient, crossing the x-axis over at 1,000,000 or something, to round about here, it feels like it's going through the origin. So in between somewhere, maybe it's gone through 2. So maybe there's one solution around here somewhere for a point which just comes downhill and hits 2, 0, perfectly like that or something. You take a line from 2 and just rest it on top of the curve or something like that. Okay, so maybe there's a solution over there, and then I'm thinking about the tangent kind of levelling out as I move A until I get to another interesting point here where the tangent is parallel to the x-axis, doesn't cross at all, and then over here the tangent can come up and maybe it can go through 2 like that. Draw a line through 2 that's just touching the curve over there. So that's interesting, and then over here the tangent's going to go through this point on the axis, on the root, and then eventually the curve, I can kind of imagine it up here being really steep and just coming back down through 2. So to take a point maybe from 2 and imagine joining it out to the curve on either side. Not quite like that line I've drawn, which is going to the left, which feels a bit unlikely, but maybe some really pair of lines going out like that. So it feels to me like there could be 3 solutions for how this line could be tangent to the curve and go through to 0, which is option D, and now I'm going to prove that it is option D by actually working out the tangent. Here's the algebra. Let's actually write down the tangent at that point. The gradient would be 3a squared minus 3 when x is equal to a, and let's make it go through the point a, a cubed minus 3a. So then the question is, when x is 2, is this 0? This is some line. I would like to know if I plug in x equals 2, do I get the right value of y? Do I go through exactly this point 2, 0? So I would need 0 to be equal to 3a squared minus 3, 2 minus a, plus a cubed minus 3a. And the question is really going to be, how many solutions does this cubic equation for a actually have? Okay, I think I need to multiply this out. Let's do that. I'll get minus 3a cubed. I'll get 6a squared plus 3a minus 6 plus an a cubed minus 3a. Let's simplify that a little bit. The a's go away, and I'll be left with, I think I want to multiply everything through by minus 1, just to make that 2a cubed at the front. That seems nicer to me. Minus 6a squared plus 6. Now, what sort of cubic is this? It's a cubic in terms of a, I'd like to know how many solutions it's got, how many roots it's got. Is it the sort of cubic that goes up and down like that, or is it the sort of cubic that has 3 roots like that? Sometimes it's hard to tell. Let's try and find the turning points. Because it seems to me that if the turning points are one above the x-axis and one below the x-axis, then we're done. So the turning points happen when 6a squared minus 12a is equal to 0, which happens, i.e. when a is 0 or a is equal to 1/2. A is 2, sorry. Trying to differentiate in my head too fast. So when a is 0 or a is 2, oh, that's good news actually, that looks like my picture. At the first one, the value at x equals, the value at a equals 0 is 6, and the value at a equals 2 is, oh my goodness, 8, 16, take away 24, plus another 6 is 0? No. The value when a is 2 is 8 times 2 is 16, take away 24 is minus 8, plus 6 is minus 2, so there's a change in value there. Maybe I could have just plugged in whole numbers to check that when a is 0, this is positive, when a is 1, this is still positive, and then when a is 2, it's negative, so there's some change of sign going on in there, and it goes through some points like this. Then maybe I could have spotted that it goes down and up again. So there are 3 solutions to that cubic in terms of a, 3 values of a. 1g, this question's about sine squared. Whenever I see a sine squared, I'm also thinking about cos squared. So I could turn any one of these sine squareds into a cos squared if I wanted to. Actually, first I've noticed that sine squared of 90, I know that sine of 90 is 1. So this term on the end here is just 1. But let's think about sine squared of 89. That's the same thing as cos squared of 1 degree. And that's interesting because sine squared and cos squared, I have a sine squared of 1 degree and I have a cos squared of 1 degree. Those things add up to 1. So now I've got an idea that I'm going to pair up these things to make 1s, and I've got this extra 1 at the end, so maybe this turns out to be 45 or 46 if I'm careful. So let's be really careful as we go in. Sine squared of 88 degrees pairs up with sine squared of 2, 3 pairs up with 87, and the rule is that those numbers inside have to add up to 90. So I'm going to keep going until I get down to sine squared of adding up to 90. Sine squared of 44 degrees is going to pair up with sine squared of 46 degrees. Those are going to pair up really nicely. Those also add up to 1. But then sine squared of 45 degrees is left on its own in the middle with nothing to pair with. So I need to think about that term in the middle on its own. Sine of 45 though, I know that sine value. That's 1 over root 2. So this thing in the middle is 1 over root 2 squared is 1/2. Okay, so not obvious, but there's this spare term right in the middle. Its value is 1/2. All of the other things, I suppose, what have I got? 44 terms on the left have paired up with 44 terms over on the right. I've got this one term in the middle, plus let's not forget the sine squared of 90. That makes overall 44 plus 1/2 plus 1, 45.5, which is option D. 1h, we're asked which of these following 5 graphs is a graph of the function y equals log base 2 of 9 minus 8 sine x minus 6 cos squared x. It would be quite hard, I think, to sketch that from nothing, but luckily we've got 5 options. So I think I want to rearrange the function inside. I could try plugging in 0 first. If I do that, then I get at x equals 0, I get y is equal to log base 2 of 9, take away nothing, take away 6 is 3. That is some sort of positive number, I think. 1 and a bit. Yep, 1 and a bit. But none of these graphs have scales on the y-axis, so that doesn't really help me. Looks like they're all positive. Okay, useless. I'm going to have to do some algebra, I think. This cos squared is equal to 1 minus sine squared. Making that change is a good idea because now the inside is going to be a quadratic in terms of sine x. If I do that very carefully, 9 take away the 6 is 3, still got the 8 sine x in the middle, and then I'll have plus 6 sine squared x. I think I want to complete the square on that quadratic to think about whether this term inside here, what's the minimum, what's the maximum. You can do that with quadratics, I suppose. Well, usually you can do either the minimum or the maximum. Let's see what happens. So let's take this quadratic inside. I think that is 6, and then I write the sine x here, and I would like to subtract something. I'm aiming for an 8. I suppose I'm aiming for an 8 over 6, because I'm going to multiply by 6. If I put a 4 over 6 in here, then when I square, I will get minus 8 over 6. The 6 will come in, and then I'll get this minus 8 sine x. That's for the cross term in the middle. I'll also get, that's 2/3. I'll also get 2/3 squared multiplied by 6, which I'll subtract. And don't forget to add the 3. Goodness me. Right, so that's sine x take away 2/3 all squared. So I think this takes some sort of minimum value. This quadratic looks positive to me. I mean, sine x, whatever it's going to do, this term in brackets is going to be positive or 0. So this thing takes a minimum value. We can minimise it when sine x is actually equal to 2/3. Sine x is equal to 2/3 at 2 points that are kind of over here somewhere to the left. So this has got two minima. So I'm looking for something with 2 minima between 0 and 180 degrees. 180 degrees is the middle of this range, something with 2 minima over here. I'm looking at these minima, and I'm looking at these minima over here. These two graphs look very similar, except maybe translated up or something. I would like to think about what happens when x is equal to one of those points. In particular, does this go negative or not? I'm going to need to think about that logarithm in a second. Okay, so when sine x is actually equal to 2/3, then the value is equal to log base 2 of, and now all of this stuff inside, I haven't really simplified this bit, have I? That's so that's 8 over 3, I think. 24 on the top, 24 on the top, 9 on the bottom is 8 over 3, minus 8 over 3 plus 3, plus 3 is 9 over 3, so this is log base 2 of 1 over 3. Log base 2 of 1 over 3 is negative, because log base 2 of 2 is 1, log base 2 of 1 is 0, log base 2 of 1/3 is negative. It's in the negative bit of the log curve. Had to think about the log curve in my head there. Let's draw the log curve. Log base 2 of x, that's 1, 1/3 is to the left. This is where log base 2 of 1/3 is negative, which means I think that I'm picking option A. Question 1I. We're told that a sequence is defined by first term 2, and then later terms are the product of all the previous terms plus 1 more. So to start off with, A0 is 2, and then A1 is the product of all previous terms, that's just 2, plus 1 is 3. And then A2, you multiply all the previous terms together, you get 6, you have 1, that's 7. And we are asked which of the following recursion relations is true about these numbers for all n bigger than or equal to 1. Something we could do is we could try plugging in 1 or 2 into these expressions. We know the values when n is 1 or 2. And if we do that, we find that all 4 of them work for n equals 1 or n equals 2. So no help there. We could calculate the next term. I think the next term turns out to be 43, because 7 times 3 is 21, times 2 is 42, plus 1 is 43, and then only one of them works, but we should still be suspicious that it's none of the above. So it's possible that even if one of the formulas works for n equals 3 as well, then it might not work for n equals 4, or it might just stop working later on as well. So that's one approach that doesn't work very well, especially because plugging in 1 and 2 is quite slow. Instead, I'd like to try and convert this relationship we've been given into, it's been given to us in words, I'd like to convert it into maths. I think I need to define something for the product of all previous terms, which sounds daft because it's just one less than an. So it's this sequence 1, 2, 6. You might have strong opinions about what those numbers are, but don't forget the next one is 42 rather than 24. Okay, the product of all previous terms. So here, maybe what should I call this? I suppose I want to call the product of all previous terms. I need to give it a name. I'm going to call it Bn. So Bn product of all the An from a product of all the AKs, I suppose, from k is 0 to n minus 1, all the previous ones. Okay, so then the B's are not too hard to understand. The rule is something like you take your An and you multiply that one by Bn. Bn was keeping track of all the products so far, and then multiply that by 3 for this new term, whatever it is, and we'll get the next term in our sequence, this Bn plus 1. Okay, and we've also been given a rule from the actual question text to say that An is supposed to be, this 3 is supposed to be one less than the Bn. So An is Bn minus 1. Oh, make that really clear, that's Bn take away 1. Okay, so my plan, I think, is to calculate these by going something like, if you know A and you know B at a point, at some value of n, then multiply them together, 42. That gives you the next value of B, and then subtract 1. One more, whoops, one more all the way through, one more, 43. Should have been a plus down here, 43 for A3. And then keep going. So that's sort of my strategy. We can use this to write this left-hand side over here as An minus 1, because Bn is the same thing as An minus 1, which looks suspiciously similar to this thing over here. And in fact, we are almost there. If I write this right-hand side as An plus 1 minus 1, then I'm almost exactly done. This is the suffixes are out by 1, so I need to shift my counting by 1 so that I get the actual relationship in the question. But this is pretty much the same thing that's going on in option B. B is in fact true for all values of n. This sequence has got a name. This is called Sylvester's sequence. You can find out more on Wikipedia. 1J, we're told that there are 4 distinct real numbers, A, B, C and D, and they've been used to define 4 points, capital A, capital B, capital C and capital D. There's a quadrilateral here, A, B, C, D. So let's try and draw that, I suppose. Like this, A, B, C, D. And we would like to know whether it has all 4 sides the same length. So let's start writing down expressions for the lengths of the sides. So the length AB here, I need to write down the difference in the x coordinates, square it, and the difference in the y coordinates, and square it. And then I should square root it. I can't be bothered to write the square root sign, so I'm going to put a squared on the left hand side here. Distances are positive, so this is going to be fine. Let's do something similar for BC squared. That's going to be C minus B squared plus D minus C squared, and something similar for CD squared. That's going to be, oh gosh, D minus C squared plus A minus D squared, and then finally for DA, that's going to be, goodness me, D minus A squared plus A minus B squared. Okay, the nice thing about laying it out like this is that some of these terms appear more than once. This C minus B squared also appears here, and the D minus C squared appears in the next 2 terms, and the A minus D squared appears in the next 2 terms. In disguise here, this D minus A, and then this B minus A squared appears in the first term and the last term. So if I'm comparing these expressions, quite often something's going to cancel out. My plan is that I'm going to compare these first 2 terms and say, are they equal to each other? I'm going to compare the middle terms and say, are they equal to each other? And I'm going to compare the last terms and say, are they equal to each other? Now, obviously, if all the sides are the same length, these should all be the same, and it doesn't matter which two I compare. But if those three things are all true, then it means that all four sides are the same length. It's okay to just check these three comparisons. If they're all equal like that, then all the sides will be the same. And I want to work down systematically like this because I've seen those shared terms in the right. So that first comparison, these two squares of side lengths are equal if and only if b minus a squared is equal to d minus c squared. This is kind of equation 1, I suppose, like first comparison. And then I'm going to have an equation 2. I would like to see whether c minus b squared is equal to a minus d squared. And then my equation 3 is just going to be checking whether d minus c squared is the same thing as a minus b squared. You see, by comparing the terms carefully, it's not too bad. I don't have two terms on the left and on the right because some of those cancel out. And in fact, surprise here, equation 3 is the same thing as equation 1, in a mild disguise that this says a minus b squared instead of b minus a squared. But that's great news. That means we just need to satisfy these first two equations, 1 and 2, and 3 will just come along for free. Whenever 1 is true, 3 is true as well. Okay, so we've got these expressions. They say that two squares are equal. Another way of saying that two squares are equal is to say that the difference between those two squares is 0. The difference of two squares factorises really nicely. And equation 1 can be rewritten as the difference, so if I write this multiplied by the sum of those things plus d minus c is equal to 0. And equation 2 can be written, I can do the same thing because that's also the difference of two squares, minus a plus d, and here c minus b, and then I write plus a minus d is equal to 0. And there's another coincidence here in that second bracket in each term, in each equation, sorry, that second bracket, those are the same up to minus signs. B here, minus b, minus a, d, minus d, minus c, and c. So if in the top row, if that term is 0, then the second one is 0 for free, because those brackets are simultaneously 0. One's just negative of the other. That means that if the first one is 0, the second one's 0, so that's enough. It's enough for that thing to be 0. If it is, then equations 1 and 2 are 0. Equation 3 is 0 for free, so then everything's equal. And in fact, the only alternative would be if b minus a minus d plus c was 0, this first bracket, and also c minus b minus a plus d was 0. That's the only way to avoid having these second brackets be the reason why this thing's 0. If we have both of those, then I could add these equations together and I would get 2 copies of c, the b's would cancel, the d's would cancel, and 2 copies of minus a, but that would mean that a is equal to c, and we were told right back at the top that they were distinct numbers, so that is not possible, and the only possibility really is for this pink underlined term b minus a plus d minus c to be 0. If you put the terms in alphabetical order and you move them all onto the right hand side, I guess, you get option D. Question 2, we're told a fact about logarithms. Logarithm of 1 minus x is equal to minus x squared over 2 minus x cubed over 3, and so on and so on and so on, for any x which is between minus 1 and 1. We're asked to choose a particular value of x between minus 1 and 1, and we're trying to show that something about log 2. To me, log 2 reminds me of log 1/2. So to get log 1/2, I would need to put in x equals 1/2. And also on the right hand side, I can see all of these powers of 2 downstairs, which will remind me of the powers of x up here. So if x is 1/2, that's going to match up. The only thing I need to check is that all the minus signs work. If I put in x equals 1/2 in part I, or in the given equation, I suppose, then I get the right sort of thing on the right hand side, but there's loads of minus signs. The minus signs are not going to be a problem though, because on the left I've got minus log 2. It's log 1/2, which is negative log 2. All my logarithms that I'm saying out loud are natural logarithms, logarithms base e, if you like. So that gives me, if I multiply through by -1, that gives me exactly the expression that I'm looking for. That's part 1. Part 2, I'm told to use part 1, that expression that we just found at the top of the screen there, and the fact that for n bigger than or equal to 4, 1 over n2 to the n, that's these terms, isn't it? If I put in 4, that's 4 times 2 to the 4, which is this thing here. And if I put in 5, that's 5 times 2 to the 5. Okay, use the fact that those are small, those are all less than 1 over 3 times 2 to the n. Do I believe that? Yes, because n is big. Okay, right, fine. Use this fact that these terms are small. This term is smaller than 1 over 3 times 2 to the 4. This term is smaller than 1 over 3 times 2 to the 5. Gosh, it's weird, isn't it? Okay, use that fact to find an integer. Oh my goodness, right, okay. Find an integer so that log 2 is less than something. I don't know about k right now, but it feels like we're proving that log 2 is less than something over here. So using the fact and part 1, we have that log 2 is less than, and I'm going to write out the first few terms. I haven't been told to do anything to them. But then when I get to this term, 1 over 4 times 2 to the 4, I've been given this fact that that is less than 1 over 3 times 2 to the 4. And then the next one is less than 1 over 3 times 2 to the 5, plus so on and so on. I'm hiding something in the ... there that I'm going to do this for every term afterwards. Okay, something about k plus 1 over 24. It's a bit weird. What do I need to do to this? So this sequence is not a geometric series, but it's almost a geometric series. I could mess around with some 3's. I could add and remove some bits to fix these terms to make them over 3 as well. I could approximate them. Is it still true over here? I'm not sure it is. No. So it's not true. You can't use the same inequality when n is less than 4. But actually, maybe I could just start my geometric series over here. If I start my geometric series over here, with this being my first term, then I get a nice geometric series from then on. So that's a slightly easier way to think about it, that these two terms are not part of the geometric series. The geometric series starts now. Maybe a clue there is that 3 times 2 to the 3 is 24, which is 24s we're dealing with here. First terms are not so bad, and then you hit this 1 over 24. If I do that, then I'll just write out some terms that I get. This is a geometric series with first term 1 and common ratio 1/2. So the sum there, using the formula for the sum of a geometric series, is 2, which gives me, I suppose this term, it was 1 over 24 multiplied by 2 for all of this infinite sum in the brackets, and this infinite sum is now a finite sum, is 1/2 plus an 1/8 plus a 12th, which is, putting everything together, 6/12ths, 3/12ths, 24ths, let's go into 24ths, 12 24ths, 3 24ths, and 2 24ths, all over 24. Oh my goodness. Which is 15, 16, 17 over 24. We're technically not quite done. I know it looks like k is 16. We do need to check this other bit over here to check that log 2 is bigger than 16 over 24. 16 over 24, also known as 2/3. Is there anything easy we can do? Well, gosh, that's less by just a tiny bit, isn't it? Let's look at the first few terms. Log 2 is clearly bigger than 1/2 plus 1/8 plus 1 over 24, the first 3 terms, and those add up to 12 over 24 plus 3 over 24 plus 1 over 24 is 16 over 24. So log 2 is definitely bigger than those things, because that's just the first 3 terms in the series, and the rest of the terms are positive. So no geometric summing for that left-hand one. K equals 16 is an example of an integer k that works in both bits of this inequality, the left bit and the right bit. Okay, log 2 is between 16 over 24 and 17 over 24. It's quite a good approximation. Part 3, the first bit, is to show that log 3 over 2 is equal to something. We had a fact at the top of the question that involved log of 1 minus x. If I use x is equal to negative 1/2, I'm using the fact here that I can plug in negative values of x, then that will become on the left there, log of 3 over 2. And on the right hand side, all of the minus signs just work out, all the 2's plug in nicely. I don't need to multiply by -1 this time. I'm doing something very similar to part 1, except just plugging in a slightly different value of x, and I get this thing on the right hand side. I'm not going to write it out again. Part 3, the next bit, I need to show that log 3 is equal to this slightly different sum. Now I have an expression for log 3 over 2, and earlier on in the question, we showed that log 2 was 1/2 plus 1 over 2 times 2 squared, a very similar expression. 4 times 2 to the 4, I think it went to 1 over 5 times 2 to the 5, plus dot dot dot, so if I add those together, then I get 1/2 plus 1/2 is equal to 1, because 1 plus 1 is 2, welcome to the Oxford Math live stream. These terms will cancel out because there's a negative sign and a plus sign, but then I'll get this 1 over 3 times 2 cubed, 1 over 3 times 2 cubed, that will be, if you add those together, 1 over 3 times 2 squared. The doubling means that you lose a factor of 2, and so on and so on. But these terms with odd numbers in are going to reinforce each other, and the terms with even numbers downstairs are going to cancel each other. To give us this expression for log 3. Part 4, we're asked to deduce that, so using the thing we just did. Log 3 is between 13 over 12 and 11 over 10. Let's do the small side of the inequality first this time. I want to work out what these fractions are. This is 1, so log 3 is bigger than 1. I think we knew that already, but log 3 is bigger than 1. Maybe we only knew that because we know that e is smaller than 3. That's a proof that e is smaller than 3, I suppose. Log 3 is bigger than 1, but it's slightly bigger than that. It's bigger than, what is that, 1 over 3 times 4 is 12. This bit here is 13 over 12. So putting these terms together, and then everything else is positive, so log 3 is bigger than 13 over 12. So we need to show that log 3 is smaller than 11 over 10, and then we're done with this part. This reminds me of the previous part of the question, or an earlier part of the question, where we showed that log 2 was smaller than 17 over 24. We did that by comparing with a geometric series, replacing a kind of sequence of numbers with a more stable controlled sequence of repeating 3's so that we could use a geometric series. I'm going to do that here as well. I'm going to say that, well, let's try this. I'm going to say that 1 over 5 times 2 to the 4 is smaller than 1 over 3 times 2 to the 4. Quick check while I think, is that true? Yes, divided by 5 makes things small. 1 over 7 times 2 to the 6 is smaller than 1 over 3 times 2 to the 6. So I could keep doing this, replace all of this increasing sequence, 5, 7, 9, 11, 13, with 3's. If I do that, then I will see that log 3 is smaller than, here's the first term, here's that next term, 3 times 2 cubed plus 1 over 3 times 2 to the 4, plus 1 over 3 times 2 to the 6, plus so on and so on and so on. These terms on the right hand side, it's not quite a geometric series because of this first time. Ignore the first term for a moment, and I will get 1 over, that's a 12th, and then this is 1 plus, this time the 2's come, that's a squared, that's a 4, that's a 6. The 2's come in pairs, so this is 1 plus 1 over 2 squared, plus 1 over 2 to the 4, plus 1 over 2 to the 6, and so on and so on and so on. It's not 2 squared, 2 cubed, 2 cubed, 2 to the 4 like it was in the previous one. The 2's come in even powers only. This is a geometric series with first term 1 and common ratio 1/4. So this is the formula for solving a geometric series is like this: 1 over 1 minus 1/4. That's 4/3. If I put 4/3 in here, then I see that log 3 is less than 1. Log 3 is less than 1 plus 1/12 times 4/3, like that. Do I mean that? Yes, I do mean that, I'm afraid, which is 10 over 9. Now, unfortunately, 10 over 9 is bigger than 11 over 10. So this is not as good as the thing we've been asked to prove. 11 over 10 is a kind of tighter bound. 10 over 9, that's a bit like proving that log 3 is less than a million. I mean, it's better than proving that log 3 is less than a million, but it's still on that side. We're asked to prove something slightly more impressive. So what we're being asked to do is to take this method, where we replace 5's and 7's with 3's, and to make it slightly more accurate, to make it slightly better. That's a very hard ask, but I suppose what we could do is, when we're approximating these fractions, we're throwing away a little bit each time. We could be less careless with that by keeping more of the terms and throwing away less each each time we do some throwing away. What I'm saying is that maybe we could keep the first three terms, and only start throwing stuff away, or approximating from the 7 onwards. Okay, so I'm going to try and do that. I'm going to try and redo all of that algebra, but replacing terms from 7 onwards, using the fact that this is less than, what do I want? I want it to match up with the previous term, so I'm going to put a 5 in here, I think. This 1 over 9 times 2 to the 8 would be less than 1 over 5 times 2 to the 8 as well. That will help it pair up with these other terms and maybe give me something nice. Okay, if I do that, then I can show that log 3 is less than 1 plus, I don't want to do anything with that 12th, and then I'll take this 1 over 5 times 2, 4, 8, 16. Goodness me. Then the geometric series starts, and it's the same geometric series that we just had, but now it's sort of starting one term later, so I've got this 1 over 50 and 30 is 80 out here, so that's pretty mad. The sum's still 4/3 inside here, and that's going to be 1 over 80 out here, so I've got 1 plus a 12th plus, that is 1/60th. So if I put everything over 60s, then I've got 60 plus 5 plus 1 over 60, which is 66 over 60, which is 11 over 10, dividing top and bottom by 6. So log 3 is less than 11 over 10. What I needed to do was to start approximating one term later, to take the same sort of idea as before, but instead of using literally the same inequality, to adapt it slightly to be one that compared to 5s later on. Okay, so that's proof that log 3 is less than 11 over 10, which is actually pretty close to 1. Okay, last part of the question, we are asked to compare 3 to the 17 and 4 to the 13. There's a trick to this. We should not try and work out these numbers, they're huge. We should compare their natural logarithms. Natural logarithm is increasing, so we can compare natural log of 3 to the 17 versus natural log of 4 to the 13. The reason I want to do that is that logarithms tend to simplify powers like this, because of that rule that you can bring down the power out the front. So we have 17 log 3 versus 13 log 4, which is bigger? Fight. So this log 4 over here, I could use the fact that 4 is 2 squared. I could maybe have written this as 2 to the 26 from the get-go to make this log 2. We know some facts about log 2 and log 3. We know that this thing over on the right-hand side is somewhere between, this thing over here is somewhere between some quite complicated fractions, but I'm going to write out the ones from before, 17 over 24 times 26, and over here 16 over 24 times 26. And on the left, I know this log 3, we just proved that log 3 is somewhere between 13 over 12 is less than 17 log 3, and 11 over 10. Okay, so if I stare at this for long enough, I might notice that some 2's cancel over here to give me 13 and 12, and then this last thing that I've written down is the same thing that I've written over here, 17 times 13 over 12. I'm not actually going to work out what those numbers are, but look, these things match, which means that I can write down the string 26 log 2 is less than 17 times 13 over 12. Goodness knows how big that fraction really is. 17 log 3. That's really good news, because it means that the one involving 4's is smaller than the one involving 3's. 3 to the 17 is bigger than 4 to the 13. Final answer. Question 3, part 1. We're told the degree of a polynomial for this question, so if we didn't know that already, the degree of the polynomial means the highest exponent, which in here would be this power of 6, because 6 is bigger than 2, and this 1 times x to the 0 is an x to the 0. Okay, so reminder of how degree works, and then we're asked about a polynomial p of x, which has a turning point at 0, 0. Very first thing we're asked to do is to explain why p of 0 equals 0. That's because you have to go through your turning point. the polynomial has value 0 when x is 0, so it must have p of 0 equals 0. We're also asked to explain why the derivative is 0, and that's because the derivative at a turning point is 0. What that means is that because this is a turning point, not just any old point on the polynomial, p prime of 0, the derivative there is 0. In a way, the fact it's a turning point is the second part of the question, and the fact that it's a point on the curve is the first part of the question. Okay, so we're also asked to explain, and this is slightly harder, why there's a polynomial q of x such that p of x sort of factorises out this x squared times q of x. That's a bit less obvious. Something we could do is to think about the coefficients of p of x. Coefficients. P of x would be, I don't know, a n x to the n if it's got degree n, plus a n minus 1 x to the n minus 1. I'm writing it out like this because I quite like bringing in a sequence, and I'm quite happy thinking about the coefficients of the polynomial as just numbers in a sequence. Maybe you don't like to think of polynomials like that, in which case fine, there are other ways to do this question too. But anyway, let's think about the information we have just talked about and how that applies to the coefficients of the polynomial. We know that p of 0 is 0, but if I plug in 0 into any polynomial, most of the powers of x are just going to give me 0, so I'm just going to get a0 on the end. So this fact that p of 0 equals 0 means that a0 is 0. In a similar way, if I try working out p prime and plugging in 0, then most of the time I'm going to get 0. This term on the end differentiates to 0. It's only this term here, this a1 x to the 1, that differentiates just enough to give me a non-zero function. But then when I plug in 0, there are not so many x's that there's still enough x's left over to actually give me the value 0 when I plug in x. Putting all that together, the derivative at 0 is just a1. And we've been told that this is 0 as well. We just proved that this is 0 as well. So what that means is that a0 is 0 and a1 is 0, and then all the other terms have a factor, a kind of shared factor, of x squared. So if we pull out that factor of x squared, we'll be left with some polynomial which I'm going to be calling q of x to match up with this question. So because this particular polynomial can't have a constant term and it can't have a linear term, this x squared factor must factorise out of our polynomial to leave us with some q of x times x squared. Part 2, we're told that a different polynomial r of x has got a turning point at a0 for some real number a. We are looking for an expression that's a bit like the one we just had for r of x, and I suppose we're asked to justify this in terms of transformation of a graph. So the previous one had a turning point at 0, 0. This new one has a turning point at a0. Let's try and draw pictures of what these could be. Maybe this is p of x, and maybe r of x has its turning point at a0. If a is positive, then maybe this looks like this coming down and having a turning point and then going back up again. Okay, so these don't look like they have any relationship between them at all, except that there's this turning point going on here. Let's label that point as a. Okay, so what I would like to do, I think, is translate r to the left so that it's the sort of polynomial we were talking about in part 1, one with the turning point at 0, 0. If I do that, so if I do r of x plus a has a turning point at 0, 0. So this is a sort of different function of x compared to the one I've actually been asked about, because I've done this translation to it. But if I do that translation to translate it a units to the left, remembering that that's the one where you add a to the argument, then I get this new function has a turning point at 0, 0. So let's be really clear. This might not be precisely the same p of x that we were imagining before. It's another example of p of x that does the same thing. So we can write r of x plus a, this translated object, is going to be x squared times q of x for some q of x polynomial. Now, this might not be the same q as your favourite polynomial p that we had before, but it's true for some q of x polynomial. Okay, and then I want to do a substitution on both sides, I think. So I want to turn this back into, I want to aim for a statement about r of x. I think I want to write u is equal to x plus a, so I'll get r of u on the left hand side, and I'll get u minus a squared, q of u minus a on the right, doing this kind of change of variables. And then I'll relabel. I'll switch my u to x. So this is not a translation or a substitution. I'm just changing which variable I talk about to make it more clear what I'm talking about. This is sort of a rule for any value of u. You can plug in any value of u on the left, so long as you get the stuff on the right where you write a u here and I write a u here. That's also true if I write it out with x's instead of u's. These two steps are subtly different. There's a translation step, there's a substitution, and then there's a relabeling. Anyway, this gives me the expression r of x is equal to x minus a squared times q of x. That's still for some polynomial q. Of course, q of x minus a is a polynomial with all the x's switched to x minus a's, which is still a polynomial. So if you like, you could write r of x is equal to x minus a squared times s of x, or something like that, for some polynomial s. And that's sort of equivalent. I mean, it's exactly equivalent, and it looks a little bit more like star, so that's also nice. I've had to bring in another letter of the alphabet, S, but the important bit here is that this r of x should have an x minus a squared times some polynomial. With that x minus a, you can think about it, I suppose, as when x is equal to a, this is 0, and then it's a repeated root for x to the value of a. Part 3, we're told that f of x has two turning points at a0 and at minus a0, and it's a polynomial of degree 4 for some a is a positive number. Okay, so it's got a turning point over on the right somewhere, and it's got a turning point over on the left somewhere. I guess it's doing something in between, and maybe it's going up at the other sides. Maybe it's got some more turning points. So my expression for f of x has got to have in it, I suppose, it's got to respect the fact that this has a turning point at a0. So f of x has got to be equal to x minus a squared times s of x for some s of x. And f of x has also got to be equal to ax plus a times, I need another letter of the alphabet, w of x for some w of x. That first one is because the previous part we talked about polynomials that have a turning point at a0, and if I just switch the a's for minus a's, then I'll get this expression for what it means to have a turning point at negative a, comma 0 as well. F of x has got to do both of these things, which feels unlikely. In fact, it means the only way to do both, given that f of x has degree 4, is polynomial degree 4, is for f of x to be equal to, I suppose it could be some number multiplied by, I want all of these terms, the x minus a squared and the x plus a squared. I can't have any more terms because the maximum degree of x is supposed to be 4, and I already have degree 4 around here. I suppose I don't know what the coefficient of x to the 4 is, but if my polynomial has factors like these ones, and also factors like these ones, that's already a lot of factors, and I don't want any more factors with x's in, I suppose. So a bunch of numbers, multiply all your numbers together to be some sort of coefficient a at the front there. That is my most general expression for f. Sort of repeated root at a, also a repeated root at minus a, and no more roots counted with either repeats or not repeats because I've got enough already, thank you very much. Part B, we just have that f of x was a times x minus a squared x plus a squared. There's a symmetry where you can flip the a's and the minus a's, but that's not a symmetry of the graph in terms of x. When you draw the graph, a is just some number. instead, what I'd like to think about is the way that this reminds me of the difference of two squares again. X squared minus a squared, all squared, and then the x squared is symmetric. You can replace the x's with minus x, so you can reflect in the y-axis. We can prove that algebraically by swapping x to minus x gives f of minus x is equal to a minus x squared minus a squared all squared. But that's the same thing as minus x squared is the same thing as x squared. So this is the same thing as f of x. So our graph has sort of nice symmetric turning points, but then also has symmetry in the y-axis. And then part C, we're asked for the x-coordinate of the third turning point of f of x. It can only have 3 turning points because when you differentiate it, you get a cubic. Cubics can only have 3 roots. From the picture I drew just now, you can maybe guess that it's in the middle. And in fact, if it was not in the middle, then its mirror image would also be a turning point. That's the thing about mirror symmetry. If it had a turning point over here, then the mirror symmetry version would give another turning point over here, which is just a bit of a mess. We would have too many turning points. 1, 2, 3, 4, too many. The only way to get around that is for that third turning point to be on the line of symmetry, so that its mirror images itself at x equals 0. That's where the third turning point must be. It's not that bad to multiply it out if you really want to multiply out the expression that we had before, and then to differentiate it and to say, aha, when x is 0, I get a solution, because you can differentiate this using facts about polynomials. So f prime x equals 0 at x equals 0. Okay, that's just another example of a turning point. And in fact, you can see from that cubic the other solutions. Oh, I've made a mess of that. These x cubes are not there, or are they x squareds? Goodness me. They are maybe just 1x. So x is 0 or x squared is equal to a squared if you get all of your algebra correct. Part 4, we're asked whether there's a polynomial of degree 4 with turning points at 0, 0, 1, 3 and 2, 0. This turning point at 0, 0 reminds me of the very first part of this question, where we agreed that that polynomial would have to be of the form x squared times some other polynomial, which, now that I know I'm talking about a polynomial of degree 4, I could write this out as ax squared plus bx plus c. And then I could try and work out whether I can find out values of a, b and c. Now if you do that and you go and solve for those coefficients, it turns out that yes, you can solve for those numbers so that it has turning points at 1, 3 and at 2, 0. But it's not very fun. So I'm going to try and do a different method where I use part 3 instead. To do that, I'm also going to notice that 2, 0 is also on the x-axis. The previous part of the question was all about having 2 turning points on the x-axis. Of course, in the previous part of the question they were at a0 and minus a0, and this time that's not what's going on, but we can translate. Remember the second part of this question, we can translate around. So I'm going to take this hypothetical curve that I'm interested in, with turning points here and about there and about there. Maybe it exists, maybe it doesn't. Picture maybe to scale, maybe not to scale. We will find out. And I'm going to translate 1 unit to the left. Do a translation. If I do that, then I'll get something hypothetical with turning points at 1, 0, minus 1, 0, and 0, 3. Now, my plan is to find this hypothetical function to prove that it actually exists, and then to imagine translating it 1 unit to the right again to get the thing that I actually want. Okay, if I do that, that is the thing from part 3, with small a equals 1, and then that amplitude, the coefficient at the front, needs to be, I think, the number 3 for this to work. So I'll get something like that from part 3. Using the fact that this last turning point does have x coordinate 0. The y coordinate I'm thinking about plugging in x equals 0 to make sure that I get the right number. But by the stuff we did in part 3, that has got a turning point there at 0, 3. So this has turning points at It has turning points at 1, 0 and minus 1, 0, because that was the whole point of the setup of part 3, and at 0, 3. 0 because we said that it has x coordinate 0, and 3 because if I plug in 0 I get 3. So it has those 3. So now I want to take this curve and translate it back 1 unit to the right to get exactly the curve I'm looking for that has turning points at 0, 0, 1, 3 and 2, 0. The way you translate to the right is you write down final answer. I need to write down x minus 1, or is it plus 1? It's either minus or plus, isn't it? When x is 1, that's what I want, I think. Okay, final answer. 3 times x minus 1 squared, take away 1. Can I simplify that a little bit? I think I can. X squared minus 2x all squared, which is then going to be 3x to the 4 minus, there's going to be a 4 in here, 12x cubed, I could multiply that out, 4 plus 12x squared, which is not so bad. That's my final polynomial for part 4. Answer, yes. Final answer. Final answer. And then last part of the question, is there a polynomial of degree 4 with turning points at 1, 6, 2, 3 and 4, 6? The answer this time is no. And to see why, let's imagine doing the same method that we just did with translations. This time the points are not at minus a 0 and a 0 at all. There are these points at 1, 6 and 4, 6. But I can translate. I can go, gosh, I want to go down by 6 units. So go down by 6 units to get turning points that are 1, 0 and 4, 0. And then go left by, I want to space them equally, so the origin's in the middle. The distance there is 3, so I want them kind of 3 over 2 on each side. So I want to get them to minus 3 over 2 and 3 over 2. How do I get that to minus 3 over 2? I guess I go 5 over 2 left. So 6 units down, minus 5 over 2 to the right. Do I mean that? 8 over 2, 5 over 2, 3 over 2. Yeah, looks good to me. Okay, if I do that, then the third turning point should now be at x equals 0, but it's not. I haven't been tracking it just now, but 2, 3, you go down by 6 units, gets you to 2 minus 3, and then if you go left by 5 over 2 units, gets you to negative 1/2, negative 3, which is not at x equals 0. In part 3, we proved that the third turning point will be slap bang in the middle, but here, this hypothetical polynomial after translation doesn't have that turning point in the middle. This means that such a polynomial can't exist. Otherwise, we could do some translations and find a counterexample to the thing we proved in part 3. So because we did the thing in part 3, we know that this polynomial in part 5 can't exist. There's also a method where you write out all of the coefficients of the polynomial. There are 5 coefficients of this polynomial, and you try and solve simultaneous equations to make it go through all 3 points and have turning points at all 3 points. It's a lot of maths that I'm not going to do on the screen now. And that is the end of the question. Question 4. Before we look at part 1, let's try to understand what's going on. So there's a cake in the question, and there's a straight line segment from xy to x0, and a second straight line segment over from xy up to 0, k. These are straight lines. We've got some region over here that's been shaded underneath. It's bounded to the left of the first cut, that's the left of this bit, and it's bounded below the second cut. This was the second cut, so we're looking at this region of the square. Wherever it says cake, it means this kind of physical square between 0 and 2 in the x dimension and 0 and 2 in the y dimension. I guess we're looking straight down on the surface of the cake and cutting a slice out of the corner. We're going to try and make that slice have a particular area, so we're going to work out the area of that shape, and then we're going to work out some inequalities to work out what the kind of limits are of what you can do by moving around, choosing this point 0k. In the question, Charlie is sort of halfway through making this cut. Charlie's done the first cut, it's about to planning to make the second cut somewhere on this edge. So k could be between 0 and 2. somewhere over there, which gives them some range, some control over the area of this slice of cake. We're going to explore that through this question. So part 1 then, we're asked to work out the area of that slice of cake. And remember, it's this sort of shape where this corner is at x, y, this corner is at 0, k, this is the origin, and this is the point x, 0. So this shape's got some right angles to it, but it's not a triangle, it's not a rectangle, it's a trapezium. Some people know a simple formula for the area of a trapezium. Even if you don't, then you could split it, I suppose, into a rectangle plus a triangle, and then it's not too hard at all. The rectangle has area xy, and the triangle has area x times, what is that, k minus y times x over 2. I don't know what I said out loud, but that's the area of that triangle. I'm not sure that knowing the trapezium formula makes it any faster to write down, because you have to get the formula right for the size of a trapezium. Okay, I can simplify this very slightly to this. I don't know if that's useful or relevant. Makes it look a bit more like the trapezium formula. Anyway, we're asked to check this expression by verifying that if x equals 1 and y equals 1, then choosing k equals 1 gives us 1/2 times 1 plus 1/2 times 1, which is equal to 1. A slice of cake with area 1. Good. Okay, for part 2, we're asked for another point on the cake, another pair of coordinates x and y, such that, so not this one, but such that, another one, such that choosing k equals 1 gives a slice of cake with area 1. So that would be, we'd need to have that area we just found, 1/2 of xy plus 1/2 of k is 1, x, would need to be 1. We've seen that 1, 1 is a solution to that, but we can do other things, I suppose. Can I guess a value? Let's try guessing what happens when I make x something else. It's got to be between 0 and 2, so I'm going to make it, let's see if I can get away with x being 1/2. If x is 1/2, then I have y over 4 plus 1 over 4 is equal to 1. So y is equal to 4 take away 1 is 3, but that's off the edge of the cake. So this is not an example of a point on the cake. Maybe I could be more systematic. I could divide both sides by x. If x is bigger than 0, to get, maybe multiply by 2 to get something like, this is something like, oh gosh, 2 over x minus 1. Okay, so I can quickly check here that putting in 1 gives me 2, gives me 1, which is what I was expecting, because this 1, 1 solution again. Putting in x is 1/2 gives me 4 take away 1 is 3, which is the same thing I just had, but still not okay. Maybe if I put in x somewhere between 1/2 and 2, and between 1/2 and 1, I'll be okay. Let's try x is 3 over 2. I have a good feeling about that because I think that's going to be on the safer side of, I'm imagining this curve coming down and flattening out, so being more likely to land on the cake somewhere. That will be y is 4/3 take away 1, I think, which is otherwise known as 1/3. That's a point on the cake. 3 over 2, 1 over 3. Other solutions do exist, of course, because there are other points on this line that lie inside the square, bounded between x's 0 and 2, y is bounded between 0 and 2. Okay, but I found mine, 3 over 2, 1 over 3. Part 3, this is now talking about what's possible when we're choosing that value of k, remembering that that point's got to be somewhere on the side of the cake, so k is between 0 and 2. That's the cake part of the question. We're looking for a slice of cake with area 1. We know a formula for this, don't we? xy over 2 plus ky over 2 is equal to 1. We're no longer saying that k has to be the number 1. We're looking at a range of values, choices of k. But we would like this to work out. We would like k to be between 0 and 2. Something we can do is to rearrange this in a way. What we were doing before is to rearrange it for y. Now I feel like rearranging it for x. So if y is non-zero, then we can do something like this. And then we can write down the fact that this is between 0 and 2. So technically this is what we want. We would need k to be 2 over y minus x, and need k to be between 0 and 2. So we would need this expression to be between 0 and 2. So this left-hand bit, because y is positive, or bigger than or equal to 0, this thing over here on the left, this left inequality, we can rearrange that by multiplying it by y to get xy is less than or equal to 2. That's the first thing. And this right-hand expression, again, because y is positive, we can multiply this one up by y to get this. And then I think that's going to rearrange to be that 2 is smaller than 2y plus xy, which is otherwise known as y2 plus x. Problem, not what was in the question. Part 3, we're now thinking about choices of k. So k doesn't have to be 1 anymore. It could be anywhere on that side of the cake, which means that k is between 0 and 2. It's going to be somewhere on the side of the cake. We're looking for a slice of cake with area 1. I need to write down the area again. That was xy over 2 plus kx over 2. And we want that to be equal to 1. Okay, so we want it to be between 0 and 1, and we need k to be between 0 and 2. This makes me think that I could rearrange this expression with k, and then try and look at the inequalities. If I do that, what would I do? I'd multiply by 2 over x. That's quite nice for both terms. And then subtract y. So this thing is k is equal to 2 over x minus y. And I need that to be between 0 and 2. 2 over x minus y. Okay, so this first term, I guess, because x is positive or equal to 0. If it's equal to 0, then there's something slightly different going on. This left equation is just true, isn't it? If x is equal to 0, and the right equation is rubbish. So maybe x equals 0 is not an example of something that works. Okay, anyway, when x is positive or equal to 0, we can multiply through by x to get this, which then on the left here says that I can keep going, can't I? I can add xy to everything, and I'll get 2x plus xy. So this first one says that 2 is bigger than xy, and this right-hand one says that 2 is less than 2x plus xy, splitting them up now into 2 separate inequalities to make them easier to work with. So this one says that 2 is small, it's less than x times 2 plus y. Okay, so those are the 2 inequalities that I've got. That lets me choose a point somewhere on the side, so that I can make the area of that slice of cake exactly equal to 1. In part 4, we're asked to sketch the region where both inequalities of part 3 hold. So these are the 2 inequalities. xy is supposed to be less than 2, and x times 2 plus y is bigger than 2, or equal to in both cases. Let's start with xy less than or equal to 2. So xy is equal to 2 on the line y equals 2 over x. Now I know that curve, that goes through 2 over 1 is 2, 2 over 1.5 is 2 over 1.5 is 4/3, call myself out there, and 2 over 2 is 1, so I need a curve that comes down and goes through both of those like that. Nice. So that's one of these inequalities, or that's the edge where one of these inequalities is equal. And the other one, I'm going to rearrange that one to be y. I'm going to think about the line. I know this is not the equality, this is some line where it's equal. This is the edge of the region that satisfies the second inequality, I suppose. It's 2 over x minus 2. So that will go through a point 2 down from here is down here. And then I need to think about what is going on. When x is very small, 2 over x is very large. So somewhere in between, this 2 over x minus 2 curve is going to come up like this. Okay, they ask us to indicate any relevant points on the edge of the cake. There are 4 that I can see. 1, 2 over here, 2, 1 over here, 1, 0 over here, and then I've got to think a little bit. This is 2 at x is equal to, I want 1/2, because then this will be 4 taken away 2 is 2. So this is 1/2, 2. Okay, and the region R this region in between, where xy is small. Let's just check it is the region in between and not weirdly the region that's outside both, which I'm not very convinced about. We want xy to be smaller than 2. This is the line where it's equal to 2, x and y are smaller on this side, and on the other side we want x and y to both be big in some sense. We want them to be bigger than the line where the product like this is equal to 2. So R is that region in between on the surface of the cake. Okay, part 5. Charlie's now got a different plan for cutting the cake, and I think I need a picture. So that first cut is the same. The first cut is the one that went from xy down to x0. It's the second cut that's different. It's now going up to m, 2. And again, we're going to follow the same steps of the previous parts of the question. We're going to work out what the area is. We're going to say we want that to be 1, and we need m to be between 0 and 2, so that this cut goes up to somewhere on the side of the cake. Okay, so that area is now a rectangle plus, I want to do a rectangle plus another rectangle plus a triangle, and I'll get something like the area, it's this area on the left that I want, which is xy plus, what is this one? It's m wide, and it is 2 minus y tall, and then this triangle at the end there is also 2 minus y tall, and its width is x minus m. I need to divide by 2. Can I do anything nice to that? I think I can write that as, so these terms have got a common factor of 2 minus y. I can write this as 2m over 2, bring it in, and then brilliantly it's going to add on to that x minus m to give me an x plus m. The effect of adding 2m for you. So I'll get this area. So I want this to be equal to 1, and I need m to be between 0 and 2. I'm going to think about the effect that that has now. So there's only one m in here. It appears here, and that m there is between 0 and 2. We know that 0 is between m and 2. We also know that we're adding x, which is somewhere between 0 and 2, dividing by 2, multiplying by 2 minus y. So y is between 0 and 2, so 2 minus y is positive, at least. Good to know, unless y is equal to 2, but hey, it's positive or equal to 0. And then we're adding on xy, which is, I suppose, also positive. So the kind of extreme cases where m is equal to 0 or m equals equal to 2, and in between we get some range of possibilities. Let's chase through what happens when m is, using the fact first that we know that m is bigger than or equal to 0. We know that m is bigger than or equal to 0, so x plus m is bigger than or equal to x plus 0, and then I can divide both sides by 2, and I can multiply both sides by 2 minus y, because 2 minus y is positive. And then I can add xy to both sides. And that's a good sequence of things to do, because I know that this thing on the left is 1. So we have 1 is bigger than 2 minus y, x over 2, plus xy, which if I multiply it up by 2 gives me 2 is bigger than or equal to 2x minus xy plus 2xy. This is xy, that's x2 plus y, which is, I think, just what we had before in the previous part of the question, or back in part 3 we found an inequality that looks like this, but now it's the other way around. So this inequality on the surface of the cake, it was this one that came down like this. It was 2 over x minus 2, I think, as the equation of the curve. It went through 1, 0 and 1/2, 2. Okay, so that's one fact we've used, that m is positive. We've also got this fact that m is bigger than, m is less than or equal to 2. That gives me another thing I can write down. That means that I can write down that x plus m is smaller than 2 plus x, because m is less than or equal to 2. I can divide both sides by 2. I can multiply both sides by 2 minus y, because 2 minus y is positive, and I can add on xy. And that's again a good sequence of things to do, because the thing on the left is exactly 1. So 1 is less than x plus 2 2 minus y over 2 plus xy. This is some equation for some region. This is the equation. Yeah, this is the equation for some region of the cake again. There's a bit of work to do to rearrange that expression for y, to sketch it onto the cake, and to work out where it is. If we do all of those steps, it turns out that it goes through this point at the top and down to 0, 1 over here. That's a little bit complicated. The region at the end is going to look like this over here. I'm going to try and recreate all that algebra now. If you don't want to see all the algebra, skip to the next question. Okay, algebra. Let's multiply up by 2 and deal with all of these terms inside brackets. There's a 2 in here as well. So what can I see? I can see a 2x, a 4, a minus xy. That's not too bad. A minus 2y and a 2xy. So that's going to remove one of these xy's. I'm going to keep my y terms on the right. I have x minus 2 of them, and I'm going to move my x terms, the remaining x terms, onto the left hand side. I've got subtract 2, I've got minus 2x minus 2. That's a bit unpleasant, but I suppose I wanted some minus signs anyway because this x minus 2 is a negative number at the moment. So if I multiply both sides by minus 1, flip the inequality, I'll get 2x plus 2 is bigger than or equal to y times 2 minus x. And now I'm feeling a bit better about this. I want to prepare the left hand side. Before I divide through by 2 minus x, I want to try and write that left hand side as something like minus 2 times 2 minus x plus 6, because I want to get that 2 minus x on the left hand side as well. I thought about how this minus 2 times minus x would give me the 2x, and minus 2 times 2 would be 4, add on another 2, add on 6 to get up to 2. Okay, so if I divide by 2 minus x, then I will get something like y is less than or equal to, so final curve that I want to draw, 6 over 2 minus x minus 2, which is some combination of translations and reflections of the 1 over x curve, I suppose. Gosh, too many to say out loud. No, reflect it, translate it, stretch it, and translate it again. My goodness, let's plug in x equals 0. We get 3 take away 2 is 1. That's the point 0, 1 that I said it went through. And it's equal to 2, that curve on the right hand side, is equal to 2 when 6 over 2 minus x is equal to 4, which happens when 2 minus x is equal to, happens when 6 over 2 minus x minus 2 to be equal to 2. That happens when 6 over 2 minus x is 4, which happens when 2 minus x is equal to 3 over 2, which is when x is equal to... Shouldn't have tried to do it out loud. When x is 1/2, y is 2, so it comes off the top of the cake up here, and the region is now y is less than that curve, so it's this region over here. Final answer for question 4. Question 5, part 1, it's time to make some triangles. We need to check that the sum of any two sides is longer than the other side. So for example, in these triangles, 3 plus 4 is bigger than 5, 5 plus 3 is bigger than 4, 5 plus 5 is bigger than 2, 5 plus 2 is bigger than 5. The sum of any two sides needs to be bigger than the other one. And these triangular triples are counted as distinct if they have the same numbers in a different order. So these ones laid out in this row here, they all use the same numbers, but those are 6 different triangular triples for this total of 10. Okay, so we're asked about the number of triangular triples for small perimeters. If the perimeter is 3, these sides have got to be positive integers. Really the only triple we should consider is 1, 1, 1, and that does work. 1 plus 1 is 2, 2 is bigger than 1, so that is a triangular triple. It's the equilateral triangle, right? There's only one example though, so f of 3 is equal to the number 1. Okay, so f is the number of these, not like a list of them or this box or a kind of perimeter or something. It's the number of things inside there. Okay, for f of 4, I suppose we need to make 4. There's not very many ways to make 4 either. The only sum I can think of is 2, 1, 1 to increase the previous one just by 1. To make 2, 1, 1, that gives perimeter 4, but that's not a triangle. It's not a triangular triple, because 2 isn't bigger than 1 plus 1. We would need the sum of two sides to be bigger than the other one. So there are no possibilities for this. perimeter, f of 4 is 0. Okay, then for 5, at this stage I think we can consider 3, 1, 1 maybe? Or, oh no, that is 5. Or maybe we could consider 2, 2, 1. I'm thinking about ways to make the previous triple just 1 and bigger. I suppose I should start from 1, 1, 1 and make it 2 bigger. Numbers that add up to 5 is a sort of sub-problem of what we're doing here. Numbers that add up to 5, you can have 1 and 1 and 3, or 1 and 2 and 2, if all of your numbers have to be whole numbers that are bigger than 0. Anyway, that 3, 1, 1 is not a triangle. 2, 1, 1 is a triangle, that's fine. The sum of the two smallest sides, 2 plus 1 is 3, that's bigger than 2, so we're fine. That's an isosceles triangle. There are then a couple more other possibilities that we should write down. Because remember, these count as distinct if we're listing them in the different orders. So f of 5 is 3. There are these 3 things in this box down here, and that means that the value of f is 3. By the time we get to 6, we've got quite a few things to consider, where we have a sequence of numbers that adds up to 6, but most of them don't work. 4 is too big, the other sides won't be able to stretch across that side of 4. 3 is actually too big as well. 2, if one side's 2, if the bigger side is 2, then the other sides have to be 2 as well, otherwise they would be bigger than that one. So 2, 2, 2 is the only one that works, and f of 6 is 1. So this is quite a complicated sequence. It goes up and down, 1, 0, 3, 1 for these terms in the sequence. The rest of the question is going to work out some more values of f. Part 2, we're told that ABC is a triangular triple. Now there's different cases depending on what order those numbers are in, but let's start by supposing that A is less than or equal to B is less than or equal to C. If ABC is a triangular triple, then switching them around so that the smallest was first will still be a triangular triple. That permutation thing again coming into play. Then triangular triple means that this is in the paragraph at the top of the question, A plus B is bigger than C. Okay. What do we want? Well, if we've got A less than or equal to B less than or equal to C, then A plus 1 is less than or equal to B plus 1 is less than or equal to C plus 1, so they're still in order on the right hand side over there. And we want A plus 1 plus B plus 1 to be bigger than C plus 1. So that's something that we want to be true. It's equivalent to saying that A plus B plus 2 is bigger than C plus 1, and now it's maybe becoming clear how we're going to prove this. We know that A plus B is bigger than C, we want to show that A plus B plus 2 is bigger than C plus 1. The proof is going to be like this. A plus B plus 2 is bigger than is bigger than C plus 2 by the fact that we know already. And that's bigger than C plus 1 just because 2 is bigger than 1. Which is the thing that we wanted over here. So A plus B plus 2 is bigger than C plus 1. Okay, so very neat, it's not very much to write down, but if A is less than or equal to B is less than or equal to C, then you can go from this triangle triple ABC to A plus 1, B plus 1, C plus 1. If they're not in order, then you can rearrange them to get them in order, add 1 to each of them, that's doing the same thing to all of them, and then rearrange them again to match up with the order they were in at the front. That's sort of semi-obvious that you can unshuffle them once you've added 1 to each of them. I'm not going to write anything on the screen, but it means that even if this bit's not true, even if they're not in order, then the same thing still works. You can add 1 to the sides of a triangle, it doesn't matter which way round the triangle is. Part 3 wants us to go the other way round, to start with X, Y and Z, a triangular triple, and to try and subtract 1 from each side. Now we've got to be careful here. In fact, we know this doesn't always work, because we know that there's triangle triples out there like 1, 1, 1, where if you subtract 1 from each side, that's no triangle at all. Or perhaps more subtly, 1, 1, 2, 1, 2, 2, which when you subtract 1 you get 0, 1, 1, which doesn't work at all. What we're going to do here is show that you can subtract 1 from each side of a triangle and still be left with a triangle, provided that the condition we're going to use is that x plus y plus z is an even number greater than or equal to 6, and the original perimeter is even at least 6. So here goes. What do we have? Let's suppose again, and this is going to be just like we did before, we suppose that x is less than or equal to y is less than or equal to z. Again, if not, shuffle them round. That's still a triangular triple. You're sort of rotating the triangle, I guess, or relabeling the sides of the triangle, perhaps. Okay, so suppose x is less than y less than z. Triangular triple. So x plus y is strictly greater than z. We're dealing with whole numbers here because everything in a triangle triple is a whole number. So these are whole numbers, x plus y bigger than z. Okay, so we're asked to show that x minus 1, y minus 1, z minus 1 is also a triangular triple. Now let's see what we want there. So it's a string of 3 whole numbers, that's fine. We want x minus 1 plus y minus 1 to be bigger than z minus 1. And that's not quite as easy as the previous thing we did. Previously we had added 2 on the big side and added 1 on the small side. Now we've subtracted 2 from the big side and subtracted 1 from the small side. There's a danger that this inequality doesn't work anymore. In general, consider numbers like 3 and 3.5. If you subtract 2 from the big side, you get down to 1.5. If you subtract 1 from the right hand side, you get to 2, and oh dear, the inequality is now the other way around. These things are whole numbers, and also this restriction about oddness and evenness in there. So this is in fact going to work. Let's see how. So we know that x plus y is bigger than z. So something we can do is that x plus y minus 1 is bigger than or equal to z. So x plus y is a whole number. Whole numbers. That's not a full sentence. If we subtract 1 from the left-hand side, we'll get another whole number, which might be z, or it might be still a number that's bigger than z. It can't be a whole number that's smaller than z, otherwise x plus y would, well, you know, it would either be z or bigger. Would be z or smaller, sorry. Oh dear. So we do actually have x plus y minus 1 is greater than or equal to z. So in fact we can write this thing. If I subtract 1 from each side, and that's fine because I'm doing the same thing to both sides. X minus 1 plus y minus 1 is bigger than or equal to z minus 1. We're almost done. We just need to check whether x minus 1 plus y minus 1 is actually equal to z minus 1. This would be a problem because then this inequality wouldn't be an inequality, it'd be inequality. We're trying to prove that x minus 1 plus y minus 1 is strictly bigger than z minus 1. Okay, if that's the case, then I think this is an oddness evenness sort of thing. X plus y would be equal to z plus 1, and what have I not used yet? I've not used the fact that x plus y plus z is equal to an even number, so I'm going to add that in now. I'm going to add a z onto both sides, just because I want to use the fact that this is an even number, whereas this is clearly odd, because it's 2z plus 1, so that's nonsense. So that we don't need to worry about that case at all. In fact, this inequality is a strict inequality. X minus 1 plus y minus 1 is bigger than z minus 1. So there's this extra bit to check that each of them is at least 2. I suppose we could show what would happen. We know the whole numbers. We could show that what would happen if one of them were 1. So if x equals 1, this is a sort of small side proof. What do we have? We have 1 plus y plus z even, and we have 1 plus y bigger than z. That's all right so far. Although I suppose if y is less than or equal to z, and 1 plus y is bigger than z, then that's a bit close. It says that y was either less than or equal to z, and then if you add just 1 to it, you get something that's bigger than z. So I suppose that means that y is equal to z is the only way this works. For 1 plus y to actually be bigger than z. Y was less than z, or equal to. So y is equal to z, but then 1 plus y plus another y even is nonsense. because that is another example of nonsense. Another example of 2y plus 1. So it's another odd number that's not even. Oddness and evenness. Part 4 links together those two previous ideas. We showed that whenever you have a triangular triple, you can add 1 to each side to get a new triangular triple. And we showed that if x plus y plus z is even and bigger than or equal to 6, you can subtract 1 from each side and get a triangular triple. That means that, subject to all of those conditions, there's a matching between triangle triples with 1 perimeter and triangular triples with perimeter 3 more, 1 on each side. This is not always true, but it is true if x plus y plus z is even and bigger than or equal to 6. So here's how it works. Let's start with this case. Suppose p is even and that p is bigger than or equal to 6. Then we'll write p is equal to 2k. So we're interested in f of 2k. That's the thing on the right hand side. It's f of p, it's the number of triangular triples with perimeter 2k. For each of those triangular triples, can subtract 1 from each side. If we do that, we get a triangular triple with perimeter 2k minus 3. So we get a triangular triple that's part 3 to say that we do get one, with perimeter it's going to have perimeter 2k minus 3 because it started with 2k and we subtracted 1 from each side. A triangular triple with perimeter 2k minus 3. But that's, in fact, we get all of the triangular triples with perimeter 2k minus 3. In fact, get all triangular triples with perimeter 2k minus 3 like this. Because if there were any left over, any other ones, we could add 1 to each side. And because part 2 says we can reverse this. We can take a small triangle and add 1 to each side, and we'll get one of these triangular triples with 2k. That's the one that we should subtract 1 from each side in order to hit that one in the small triangle collection. So the number is the same. And the number is f of 2k minus 3 for the small ones, and it's f of 2k for the big ones. And for each of these, there's one of those. For each of those, there's one of these. They match up. The functions are equal. Part 5. We're now writing p equal to s, and we're supposing that p is bigger than or equal to 6 for part 5. Okay, in this case, we're going to show something about triangular triples. We're going to find some inequalities on the side lengths. So here's how this is going to work. We know the perimeter. We want to show that none of the sides can be too big. So let's say for example, suppose C was bigger than or equal to S. Now, what do I want? I know a fact about a plus b plus c, so I'm going to try adding a plus b to both sides. I know that on the left that's equal to 2s. So I can subtract an s, and I've proved that, so for all of this, a plus b is less than or equal to s, but c is bigger than s, and that now a plus b is less than or equal to s. So a plus b at best could be equal to c, but it's less than or equal to c. That will be not a triangular triple. So that's crazy. So c must be smaller than or equal to s. And also, same thing for a and b. Repeat this with the letters the other way around for a and b. Same for a and for b. Okay, there's this other part to check that if they're all strictly smaller than S, but I suppose we still need to require the sum to add up to P, otherwise they definitely can't be a triangular triple with perimeter P, if they're all 1 or something. If they're all strictly smaller than S, then this works. So now we know that all of them are strictly smaller than S. So we know that A is strictly smaller than S, B is strictly smaller than S, C is strictly smaller than S, and we still know that A plus B plus C is equal to 2S. So what are we trying to check? We're trying to check that this is a triangular triple. Anything that adds up to 2S with all of these numbers not too big works as a triangular triple. So we need to check. Let's suppose A is less than B, less than C. If not, shuffle them around and talk about that triangular triple, or that sequence of numbers we're going to show as a triangular triple. We want to show that A plus B is bigger than C. Is that obvious right now? I would say no, that's not obvious right now. Let's try plugging in what we know into the expression that we've got. So we know that C is less than S, so over here we can say that A plus B must be bigger than S. Right, let's work that out. A plus B is 2S minus C. C is small, C is smaller than S, so this is big, this is bigger than S. So A plus B is bigger than S. That's because C is small. I'm working with this statement over here. But now we've got A plus B is bigger than S, and we still know that C is smaller than S. So C is smaller than A plus B because they're separated by S. Brilliant, so we've shown that A plus B is bigger than C. Same thing for other combinations of letters, rotate the letters around, or just relax the assumption that A is less than or equal to B is less than or equal to C by permuting them, and that shows that it is a triangular triple. Oops, there we go. Okay, so now we've understood triangular triples, I think, quite well. If we put this together, this says that in the case where you're looking at P even, 2 times S, what you need is 3 numbers to be the sides of your triangle. They can't be too big. If they're bigger than S, half the perimeter, then it's a no-go. You can't make a triangular triple like that. But if they're smaller than S and the sum is correct, then you're fine. That's a triangular triple. They will satisfy that inequality and you can make a triangle out of them. So now we really, to understand how many of these there are, we just need to understand how many ways there are to have A less than S, B less than S, C less than S, but all of them adding up to 2S. And that's the next part of the question. 5 part B, we're looking for the number of possible values of B such that, and then this is the triangular triple ABC, but for C we've replaced that value C with P minus A minus B, which is another expression because we know that the perimeter has to be A plus B plus C. The number of possible values of B such that that's a triangular triple. Okay, and A, we've been given some limits here. It's bigger than or equal to 2 because that's where we start. We know from part one of the earlier parts, part 3, that given even perimeter, each side has to be bigger than or equal to bigger than or equal to 2. So we're told that A is between 2 and S minus 1. We're interested in the number of values of B. Now, what do we know? We know that A, B and C all have to be less than S. That was our rule for making sure we get a triangular triple. A has been taken care of because we've made sure that A only goes up to S minus 1 at most. I'm interested in this B being smaller than S ruled. That tells me that B, I suppose I can write that as B less than or equal to S minus 1 if I want to match up with this inequality that we've got over here. These are separate. So then the one I haven't joined in with yet, I suppose, is C less than S, which I could write as 2S minus A minus B is less than S, which, using the fact that P is equal to 2S. Now, let's see. This looks like a rule about how big B can be. it says that b has to be large in a way. If I rearrange this, b has to be larger than s minus a, which I suppose I can write as b bigger than or equal to s minus a plus 1. Okay, so there are some possible values of b. B could be s minus a plus 1, or s minus a plus 2, or all the way up to s minus 1. Now the challenge is I need to count how many of these there are. This is the sort of minimum value of b to get this inequality to work. This is the maximum value of b. We've got a restriction on a already. We're thinking about a between 2 and s minus 1. And these are my possible values of b. Goodness me. I think it makes slightly more sense if you count from this end. S minus 1, S minus 2, S minus A minus 2, S minus A minus 1. Maybe that makes it a little bit more clearer. I've also put some brackets around here to say that there are A minus 1 of these possibilities. So remember, we're trying to find triangular triples. We've got some restrictions on A, B and C. We know that no side can be too big. And we've said that if you fix A, there's only a few possibilities for B. The number involves A. The number is A minus 1. That's how many possibilities there are for B. But we're doing quite well now because we can just think about all the different possibilities for A. A could be 2, in which case that number of possibilities for B, each of these leads to a triangular triple, is 1. A could be 3, in which case the number of possibilities, I need to stop writing out the word possibilities, is 2. All the way up to A could be S minus 1, in which case the number is S minus 2. The rule is you subtract 1 from the value of A. So that's how many possibilities we get. All of these give us different triangular triples because we're changing A and then sort of running through the possible values of B. We're sort of listing them alphabetically, if you like. Changing A first and then changing B within that list. And then making sure that C gets the total perimeter correct. This sum over here on the right hand side, I want to add all of these up. Add these up. That's an arithmetic progression, 1, 2, 3, 4. It's the sum of the first integers up to s minus 2. I've seen this sum before. It works like this. You write down n plus 1 divided by 2. That's the triangle numbers. Here, that's s minus 2 for the last term. S minus 1 all over 2, which gives me some pretty neat formula for the number of triangular triples. Amazingly, f of p for even p bigger than or equal to 6. And part 6, the very last part of this question, wants us to find f of 21. So we can use the previous parts of the question here. This is equal to f of 24 using part 4, which was the f of 2k is equal to f of 2k minus 3. That works because 24 is even. And then we can use our formula for that last part to say that this is s minus 1, excuse me, so this is p is 24, s is 12. My formula was s minus 1 multiplied by s minus 2 all divided by 2, which is 55, which is quite a few, but maybe not as many as I might have guessed. 55 triangles with perimeter 21. And that's the end of question 5. Question 6. We've got a definition here of a sorted table, one where the rows are in increasing order and also the columns are in increasing order, so the numbers there increase whichever way you go, to the right or down. So the very first thing we're asked is where the third smallest entry can appear. They've told us that the second smallest entry can't be in the top left corner because that's the smallest number, but it can be in either cell 2-1 or in cell 1-2. And now we're asked to find out where the third one is. So I suppose it can't be in the top left corner because that's definitely the smallest number. Could it be the second number down? So I know they told us that could be the second smallest number, but I suppose they weren't saying that was definitely the second smallest number. For example, in this left one, 3, 12, 15, this is the third smallest number because the kind of second one is hiding out of the way over here, so maybe this is the third smallest. In this one, the third smallest number is here, in the space 1, 2. Okay, so it's either 1, 2 or 2, 1, maybe some other things. because I suppose this 12 could be a 22, and if it's a 22, then the third smallest number is down here. There's nothing to stop this being a 22, I think. So the third smallest number could be in 3, 1 or 1, 3, I suppose. Flipping the columns and rows. They've told us that m and n are both bigger than 3, so these things exist. It can't be any further down, because then it would be bigger than all of the things above it. It can't be any further right, because then it would be bigger than all the things to the left of it. And it can't be in 2, 2, because then it would be bigger than 3 other things. Bigger than this thing to its left, because the rows are sorted. Bigger than this thing above it, because the columns are sorted. Or bigger than the thing to the left and above it, because of 2 reasons. You can read across to work out why it's smaller across and then up. Okay, so not there, not anywhere else. So the first row, somewhere between 2 or 3. In the second row, only here. In the third row, only here. And then I'm not interested in any more rows. That felt quite systematic looking through the rows. Those are all the possibilities. And then the next part of the question is to do that for the kth smallest entry instead of just the third smallest entry. They say justify your answer, so I should be careful, I suppose. We've been given quite a lot of rows and columns to play with. They're both bigger than k, so that means I suppose that it could be in 1, k. That's one possibility, like along the first row. Wait until you get to the kth biggest number. Everything else could be enormous, much bigger than that. Similarly, you could go down the first column until you find the kth thing there. That could be the kth biggest thing, because everything else could just be 100 times bigger than the thing to its left. So these are possibilities. I think there are some more though. I'm interested in that way. We were talking about the top left corner, and we said that this thing here is bigger than the stuff to its left of it, and the stuff that's above it, and the stuff above left of it, for 2 reasons. That means that if if ij, so if I'm looking at a cell ij, if ij, maybe not both 2, but if I and j both too big, then I and j are both too big, then this thing is maybe the 4th smallest thing, but it can't be the 3rd smallest thing. So if the number of things in this grid, let's make it look more like a grid, that'll help me out. If the number of things in this grid is too large, bigger than k, then not here. And the kth smallest thing is not here, because there are enough other things that I don't think this could be the kth one. It would be at least the ijth biggest thing, and that's bigger than k. Not here, so we need ij to be less than or equal to k, and that is in fact enough. The things that it's definitely bigger than are the things in that kind of top left rectangle, including itself, I suppose. Everything else could be everything else could be larger, except I need some other elements, don't I? I need some other elements to make sure that this is actually the kth smallest thing. So let's take its ij corner. There are loads of things up here. We're looking at this. We need to make sure this is actually the kth smallest thing. There are ij things that are smaller than it, or it. We need to make sure that there are another k minus ij things that are smaller than k. They could be over here, potentially. They could be over here. The row is wide enough, and there are enough things that those could all be smaller, but then the next one is just a little bit bigger than this target item in position ij. And similarly, everything else could be huge. I think that's where I can hide some extra items to make sure that this is actually the kth smallest thing. Writing that all up formally makes it quite messy to explain where these items are, that they go over here after I. Checking that that's less than k is, I suppose, something to do as well. Part 2 wants us to try and find an element y to decide whether it's in the table or not. We're not supposed to look at every element in the table. M times n is probably bigger than n plus 1, n plus n minus 1. So we can't look everywhere. We've got to be a bit systematic, and we're going to have to justify that our procedure is good enough. There's a hint to look at the top right cell. What do we know about the top right cell? Well, the top right cell is bigger than everything in the row because the row is sorted, and this top right cell is smaller than everything in that column because the column is sorted. So it's sort of in an interesting position that it's bigger than some stuff, it's smaller than some stuff. Let's think about the rest of the table. I don't think I can say anything about the rest of the table because the rest of the table could be increasing faster than the top row is, or it could be increasing slower than the top row is. But what I can say is that this top right element is bigger than everything else in its row, and it's smaller than everything else in its column. Okay, let's think about some sort of logical procedure here. So my procedure is going to work like this. Look at the top right cell. If that's y, stop. And I suppose answer is yes. Y is in my table. I found it already. Otherwise, I suppose if that's less than y, then I can say something, right? If this number up here is too small, then there's no point looking at the rest of the row because the rest of the row is even smaller. So eliminate top row. If, and this is the last case here in my three cases, if that is bigger than y, then this is too big, and also everything in the column is too big as well, because the column's sorted. There's no chance that any of these are y, so eliminate far right column. Okay, and then I think if you're still going after you've checked this and you haven't found y yet, my step here is going to be repeat this process until you either find y, you either stopped, or have no table left. So if y is in your table, then every step you're eliminating things that are definitely not y. So if you eliminate everything, then you kind of eliminated y at any step. Everything's gone now if you've got no table left. And you're eliminating everything for good reasons. You definitely haven't eliminated y by mistake. So if you've got nothing left, then the answer is no. Is no down in this right hand corner. If you have absolutely no table left. If you find y, then you should stop because you found it. I think it's quite nice that this procedure stops by actually inspecting an element and saying, oh, there it is, found it. It sort of walks towards that element, I suppose. One way to think about this is to not destroy any bits of the table, but just to walk left and down, making appropriate choices to walk in the kind of direction where you might expect to find y, one step at a time, following your nose along the way. If you're looking for a bigger number, go down. If you're looking for a smaller number, go left. If y's in there, then you will find it. Okay, this is the right number of steps because I will only inspect things. How many elements do I need to inspect? There are m rows, n columns, so m plus n, but my eliminations mean that I eliminate the last cell for free. It's 1 by 1, but I eliminate it all at once. There's a little efficiency there in that I stop when it's 0 by 1 rather than stopping when it's 0 by 0. That saves me one step that you might not have guessed, that I don't have to eliminate all n columns and all n rows. I can stop when it's 1 by 0 or something like that. So I never quite get down to 0 by 0. That saves me a step and means that there are n plus n minus 1 steps at most, and it returns whether there's y in the table or not. I'm not sure anybody needs to watch this part of the video. I should probably just show you the solution, but I thought it might be fun to have a part of the video where it's just me sorting numbers, so I'm going to do that now. Feel free to skip on to the next part. Table B makes table A by rearranging the entries in each row, so I need to sort the entries in each row. Here I go, 8 is the smallest thing I can see there, then 25, then 26, then 37, and then 22, 40, 49, 81, and then table C is obtained from table B by rearranging the elements in each column, 22, 24, 25, 33, 40, 26, 46, 49, 37, 81, 92. And if I can read my own handwriting, I think I've now got table C. Okay, part 4, the argument is quite involved, so I'm going to try and show you on this example that we had. That example is sorted. We're going to try and prove that it always happens, only using things that we know from the way it was made. So the columns are obviously sorted, because that's the thing we did to make C out of B. Don't have to worry about those, they're definitely sorted. Are the rows sorted? I mean, if you look at C, they are. For example, 81 is bigger than 46 as numbers, but can I prove that 81 is bigger than 46? Not as numbers, prove that it's not a coincidence that the big number's on the right. That would be a step towards showing that these rows are sorted. You see, we didn't really compare 81 and 46 while we were sorting. 81 back when we were looking at the rows to make B, we didn't compare 81 and 46 at all, and when we were making the column here, we did some stuff with 81 and we did some stuff with 46, but it feels a little bit like a coincidence that they've ended up next to each other. Let's see if we can piece together what's happened. So 81, I know, is bigger than 37. That's not a coincidence, that's because the column is sorted. I want to try and prove that 81 is bigger than 46, so I'm thinking about things that 81 is bigger than. It's bigger than 37. And that's a bit of a dead end, because now I'm over at 37. And 37 is actually smaller than 46, so this is not feeling like a successful proof that 81 is bigger than 46. But let's look back at B, where, what can I say about B? Well, in B I've got an example where 37, that number I was interested in, is bigger than 26, because the rows of B are sorted, and over here we have the fact that 81 is bigger than 49. So those columns get sorted independently. We don't look at the next column along when we're sorting this one, and we don't look at the previous column when we're sorting this one, but I know that 81's bigger than something in this column. I'm not certain where it's gone, but I know that 81 is bigger than 49, which is in there somewhere. So in this case, 49's gone down here, which is interesting. And I still know that 37 is bigger than 26, so that's this over here. So the things I know are that 81 is bigger than the things in its column above it, and I know that each of those was bigger than something in the column to the left. But now maybe you can see that I'm done using the rules that C is sorted, because I can pick up on the fact that 49 here is below 46 in the positions in the table. That means that 49 is bigger than 46 because the columns are sorted in C, and then I'm done. I found an example where 81 is bigger than something, and that's bigger than 46, the number to its left. So I'm going to try and piece together why it's okay to do that in a sort of general case. I think I'm going to start by showing you some sort of general notation for where that item is. And in general, I don't just want to compare things that are one to the left, but maybe I could start like that and try and build up. Okay, so let's consider the item at ij versus the item the ith row, the j minus 1th column, to go just to the left. I'd like to prove that the first one is bigger. So we're considering sort of the elements at ij and j minus 1. So here's the plan. Look at the that's the number of them, elements in rows 1, 2, 3 up to I in column J. These are the things like 37 and 81 over here. Those I things, each of them was bigger than something, I'm not sure what, but bigger than something in column J minus 1 back in table B. Back in the days when it was in B, those things were in the columns and they were bigger than because the rows had just been sorted to make B. So each of them was bigger than something in column J minus 1. Look at those somethings. Now, I claim that at least one of them, like how 49 was down here, at least one of them is far down enough that it's interesting to me. At least one is in C in row I or more. They can't all be in the first I minus 1 rows because there are I of them. So maybe they're the first ones, maybe this 49 could have turned up here, in which case it's also fine, or maybe it's further down. Pick one of those. Okay, so the item in IJ is bigger than or equal to the item, one of the items in its column, which is bigger than a corresponding item from the J minus 1th column, which is then bigger than the thing to the left of our original cell. That's bigger than, or I mean possibly or equal to, depending on if it is that item, the item at I J minus 1. It's sort of been shuffled down far enough that I can conclude that it's bigger than or maybe equal to the item just to the left. And then I'm done because I've realised that if I can compare one to the left, I can keep comparing to string this together. And that means that the row is sorted as well. And this is true for any I and J. I suppose I need J to be, I need J to be bigger than or equal to 2, so that I'm talking about actual columns that exist, counting from 1. But that's enough to prove that the rows are sorted. And if the rows are sorted and the columns are sorted, then the table is sorted. That's question 6. Question 7 gives us the definition of some special Boolean functions. Those are ones that take inputs that are either 0 or 1, and the outputs are also either 0 or 1 in each case, depending on the inputs, I suppose. Here's some examples. The min function takes any number of inputs, and it gives 1 exactly when each of the inputs is 1. Okay, and otherwise 0. The function max can take any number of inputs, and it outputs 1 exactly when at least one of its inputs is 1. As soon as one of them is 1, it says 1. It gives the maximum of all of those numbers. The function flip takes a simple input and gives 1 if the input was 0 and 0 if the input was 1. That's 1 minus x1 is a sort of strange way to write that, but it takes 1s and gives 0s, and it takes 0s and it gives 1s. Okay, we're going to combine those together to make, for example, this function min of max of the 3 variables, flip min 3 variables. My goodness. Describe in words when it outputs 1 and when it outputs 0. My goodness. So, 0 and 1 are the only things it can output, so let's not worry about too much those two different cases. We will get there. When is min equal to, let's say, 1? It's 1 when exactly all of its inputs are 1. So, f is 1 if max of those 3 things is 1 and flip of min is 1. This is not quite in words yet. I'll do it out loud. I'll do it out loud in words in a moment. So I need the maximum to be 1. So that means not all zeros. And I need flip of the min. I need the min to be 0. So that means not all 1s. Okay. So, in words, the function returns 1 if at least one of the inputs is a 0 and at least one of the inputs is a 1, and it returns 0 otherwise. Or said differently, if the inputs don't all match, it returns 1. Maybe even more neatly, if the inputs all match, it returns 0, otherwise 1. Okay, now we're going to build something called a majority function. It takes k inputs, and it returns 1 exactly when strictly greater than k over 2 of its inputs are 1. How can we make functions like this? So majority of x1, x2, it is 1 when, Oh, is it 1 exactly when strictly greater than 1 greater than one of its inputs are 1. That means both of its inputs are 1, which is the behaviour. If both of your inputs are 1, you give 1 back, otherwise you say 0, and that's 0 if you see 1 and a 0 or 2 zeros. I think that's min. That's min of x1, x2. That does the same thing. If they're both 1, it gives 1, otherwise it gives 0. Okay, majority of x1, x2, x3, this is supposed to be 1 if 2 or 3 of them are 1 and 0 otherwise. Okay, so I suppose it needs to check whether the first two, so it's okay if all 3 are 1, so I don't need to worry too much, but maybe I want to look at the first 2 and check, are these 2 both 1? If they're both 1, then we should return 1, because we've got a kind of majority just from those 2. If both of them are 1, well, what's 1 if both of them are 1 and 0? Otherwise that's min again. So maybe I could take this one is 1 if the first 2. I'm also sort of thinking of min of the other pairs as well. This is not a function yet, this is a list of functions, list of demands. I've got these 3 things. Each is 1 if a pair is 1, and it's 0 otherwise. What do I need? I need 1 of these. I only need 1 of these to work. So sort of or this, or this, or this. That's max, isn't it? So that's max of these 3 inputs. So it's sort of like building with and OR gates, if you're familiar with those. Otherwise, it's combining together the 2 things that we were given, which is min and max. I haven't used any flips in this. Never mind. Okay, I think that works as a majority gate with 3 inputs. There are other possibilities. I can't think of any immediately. Part 3, we're now asked to try and build Boolean functions with 2 input variables using majority functions that take 3 inputs. Combining 1 or more majority functions, my goodness, of 3 inputs. We're going to write our answers in terms of majority functions. There's this comment that there are exactly 16 distinct Boolean functions, which it's not that many. I suppose they have 2 input variables that could be 0, 0, 0, 1, 1, 0, or 1, 1. And then in each of these cases, they could return either 0 or 1. So there's sort of 2 possibilities. They can make sort of these choices independently for what they're going to do in each of these 4 cases. These are the only 4 cases they need to be ready for. So they're kind of 2 to the 4, which is 16 possibilities of what they do in all of these possible cases. So there's only actually 16 of these functions. It's not that many. They give us an example of how to build the function max x1, x2, which we've seen before, to build that using majority x1, x2, 1, which I've got to think about, to be honest. If one of them's 1, then the majority of these things are 1, so it passes. If they're both 0, then it fails and returns 0. So again, the majority vote only wins if, well, it only needs 1 of them, which is just like maximum does. Okay, perhaps the obvious one to check next to see what happens is maybe majority of x1, x2, 0, to see what that one does. So now if both of them are 1, then the majority vote passes, and we get something that's 1. Otherwise it fails. That's again the same behaviour we've seen several times for the minimum function. That's min x1, x2. So that's nice, we've made one thing. There are some other things we could do. We're allowed to pass 0 or 1 as fixed inputs in here. So we can imagine passing some rather strange functions like this, with 1s or 0s as both of the inputs. That returns 1, well no, that just returns 1. That's allowed. That's one of the possibilities. Nobody's telling these Boolean functions that they have to do different things in different cases, so the particular case where it just always returns 1 is allowed. It's not a very interesting function, it's constant. But yeah, it doesn't care what x1 is doing, it's going to return 1. And I can build it out of majority functions like this. Can I build the others? Let's see, that's given me the idea for this rather daft function that gives 0 always. Here's a function. It's kind of got two input variables. It's going to ignore one of them and then super ignore the other one. Yeah, 0 always. I've sort of got two input variables, doesn't really respect either of them, but functions don't have to respect, they just have to have one of these cases up here. Can I do anything else? I suppose I could put more x1s in. Let's think. So if I put more 1s and 0s in, then it's just going to ignore x1 and x2, and I think I've exhausted those possibilities. I can put more x1s in, but as soon as I put 2 of them in, it feels a bit like they're going to dominate the voting. If they're 1, it passes. If they're 0, it fails. So I don't think it matters what I put here. So this is same as x1, the function that does whatever x1 says and ignores whatever x2 is. To show you on my chart up here, that would be 0, 0, 1, 1. That's allowed, that's a function. It's a plan for what to return in each of these 4 cases. It happens to completely ignore x2, but that's fine. That's still a function with 2 inputs that ignores one of them. And that's a function that I can make. These are descriptions rather than actual functions on the right hand side, but hey, those 4 things built out of majority functions. I suppose I could do same as x2 as another one down the bottom here, and I think that might be all of the ones that you can build using majority functions. Part 4 wants us to think about another example of a function with 2 input variables, but this time it should be one that cannot be made by combining majority functions together. I suppose we'll have to string these together. I haven't really thought about these yet, but I suppose you could take, when they say combinations, I suppose they're imagining majority of things like this. Or messes like this where it's embedded in majority functions into the other one. There's this key idea about how majorities behave, in that when you have a majority, it doesn't matter if you get some extra 1s in there, it stays a majority. So adding extra 1s for a case that was going to output 1 anyway shouldn't change anything. It should stay as a majority. And that property kind of transfers from these kind of nested majority functions. If this was already 1 and we've decided it's going to stay being 1, then this one thing should stay being the same thing as well, right? The outer majority functions don't even see any changes. Okay, so maybe our example of an input function should be something that changes quite a lot. My plan for this is to, I suppose, write down something that's not a constant function. We made the constant functions already. What do I want to do then? Maybe I should specify, I've got to specify these 4 values, so that the more 1s you put in, maybe the worse it gets. So maybe this one is 1, and this one is, I'm a bit worried about flip, but we're just making things out of majority functions. This one is 1, and then this one is 1, but then this one, oops, this one is 0. So this doesn't feel like a majority, because if both of those inputs are 1, then any majority functions that were going to be on are now on, because you couldn't possibly have any more 1s in. So anything that was going to be 1 is now 1, but the final answer I want to be a 0. That's impossible. If it was going to be 1 at all ever, then putting extra 1s in should have made these majority functions just stay being 1, so the output shouldn't change. There shouldn't be a threshold. I suppose you could look at this as being, the 1, 1 comes from either changing this or changing this. Shouldn't have changed things. From a 1 to a 0. It can't decrease the value. Okay, last part of the question splits in 2. We're now thinking about combining Boolean functions or majority functions, and we're given some new letters of the alphabet. We've got 4 input variables now, x1, x2, x3 and x4, and we're told to define z1 as the minimum of the first 2, z2 the minimum of the second and third, z3 and then z4 as the minimum of the fourth and first. Sometimes you can represent your original function on the x variables by using a different function that looks just at the z variables. So it sort of does some pre-computation to work out those z variables, and then just from those z variables it can get the right answers every time. For example, the minimum of those things is just the same thing as the minimum of the z's. They both only output 1 if, in a very particular case, the right hand side, this is the z version, only outputs 1 if all the z's are 1, and if all the z's are 1, that means that each of these minimums is 1, so all the x's were 1. That's the only case. And that's also when minimum of the original function, that thing was 1. Okay, the question is, can we do that? Can we take our functions our functions on x's and write them as some sort of function with z inputs? Justify your answers. The first one is, if we're interested in the majority function, which is, it's a strict majority, so it's looking for want 3 or 4 to be 1, to return 1. That's when it returns 1. I said that very strangely. Can we build that out of z's? So, goodness. If all 4 of them are 1, I'm not going to worry. They're all 1. The z's will all be 1, and probably the function that I write down will just be okay with that, and it will return 1. Now I want to think about having 3 of them. So I suppose I could do something like I did before and look at what happens in the different cases. So if 3 of them are 1 and 1 of them is 0, 3 1s 1 0, then 2 of the z's, these are the x variables, 2 of the z's are 1 and 2 of the z's are 0, and 2 of them get taken out because each x appears twice and ruins that minimum. The other ones are 1s. I think that's okay. I think we can build something that detects 2 1s amongst the z's, or 4 1s, because if all the x's are 1s, all the z's are 1s. So I want to detect either 2 1s or 4 1s. Maybe 3 1s can never happen. Let's just quickly check. If x has just 2 1s, can it trigger any of these z's? I think it can trigger at most one z switches on. And if x has just 1 1 or even none, then this is none of the z's light up. Okay. So this looks promising. I can just build something that detects whether 2 or 4 of the z are equal to 1, because those are the cases I'm interested in, where this majority will pass if I have 3 votes for the x's, which will switch on 2 of the z's, which is not that many, but it's better than if there were fewer votes in the original x problem. So something that switches on if any 2 of the z's are 1. That's very similar to something we had before, isn't it? So if any 2 of the z's, so I'm going to look at all 6 pairs, all 6 pairs, maybe I won't write them all out, all 6 pairs of the min, looking at z up to z3, z4, all 6 pairs, and then take the maximum of all of that. And if the max switches on, that's because one of these is switched on, because those 2 z's have switched on, which only happens if you had at least 3 x's to start off with, so it passes. So that's my expression. There are other examples. For example, just writing down majority of z1, z2, z3, z4, 1 works, because if you're looking for 2 or more of the z's, that's the sort of things majority functions look for. They look for a certain number of things to work. 2 out of 4 is annoyingly not a strict majority, but you can throw an extra 1 in there to break the tie. Majority with 5 inputs works as well. Okay, and part B at the end here asks us about the parity function, which outputs 1 exactly when an odd number of its inputs are 1. And now we're doomed. We cannot write this in terms of z's, because the case where all the x's are 0 is supposed to be different from the case where exactly one of them is 1. Parity returns different things in those cases. But from the point of view of the z's, oh no, all of the z's are calculated to be 0 in both of those cases. If all the x's are zeros, all the z's are zeros. And if just one of the x's is 1, all of the z's are still zeros. They haven't switched on, they haven't woken up. That's terrible. It means the parity function was expecting a change, but nothing you write in terms of z's will be able to detect that change. You've kind of lost the information in the translation from x's to z's before you start writing down any Boolean min, max, majority, flip stuff on the other side. So there's no way to detect that tiny bit change from just one of them switching on. And that's an example of something that you can't write using these z's. And that's the end of question 7, and that's the end of Math 2021. Thanks for watching.